Okay, so welcome to Chapter 5. Chapter 5, Section 1, Areas and Distances. In this section, we're going to explore the idea of using antiderivatives as a method to calculate area, and then, once we get to area, then we'll start taking a look at what applications of that area might be. But specifically, we're going to take a look at finding area. So we're going to be using antiderivatives to find the area under a curve. Now you might be wondering what we mean by that when we say area under a curve. So essentially what we're looking at here is we're looking at a situation like this, where you're going to have some function, y equals f of x. We are going to have some lower limit that we usually call a, some upper limit that we usually call b, and our job is going to be to calculate the area that is encapsulated or trapped or bounded by the function above, the x-axis below, the line x equals a on the left, and the line x equals b on the right. And the reason that we need calculus for this is because geometry fails us. Geometry has lots of applications where you can find the area of regular shapes. If you have a rectangle, you know that the area is length times width. And if you had a circle, you know that the area is pi r squared. And if you had other geometric shapes, there are formulas for them. If you know that you have a triangle and you've got a height and a base, you know that the area is equal to 1/2 the base times the height. And so geometry is really good as long as the shape is something that we know, something that we've experienced before or worked with. But as soon as we fall into the category of trying to figure out what to do when we have a shape that is not a regular geometric shape, well, geometry becomes useless and we need something else. Now, these three sides are straight, so that's good. But because this top part is curved, we need something more than geometry. And that something more works out to be calculus. Okay? And so what we're going to do is we're going to use something called a Reimann summation as a technique for making this work. So let me get rid of all this because I'm going to need that space later. But what we're going to do is we are going to find the area under the curve by first doing an approximation technique, and then we're going to refine that approximation technique, refine it, make it better, until it gets so good that it ceases to be an approximation and becomes the exact value. Okay? So we are going to take the limit as the approximations get better and better and better and better and better until that approximation again ceases to be an approximation and turns into the exact value of that. Okay? This process is called finding a Reimann sum or a Reimann summation. Riemann's the name of the guy who did a lot of the pioneering work with it. And the reason it's a sum is because we're going to break the area up into pieces and add those together. So it's a method of approximating the area under a curve. So it's a method for approximating the area by dividing the area into rectangles. And each of those rectangles then is easy to find area for because rectangles are length times width, length times width, length times width. So essentially what's going to happen is someone is going to hand you the necessary information. The necessary information being an equation for your function y equals f of x. So the algebra for that. They're going to hand you the value for a that you're going to start this at. They're going to hand you the value for b that they're going to start this at. And they're going to hand you the number of rectangles to break this up into. And then you're going to come over here, you're going to say, okay, well, if they want me to say break this up into, and let's just make up one, let's say they want us to break this up into 3. I would divide this into 3 pieces. I'd square off the tops of them. I'd find the area of the first rectangle. I'd find the area of the second rectangle. I'd find the area of the third rectangle. I'd add those 3 areas together and say the approximate area under that curve is the sum of those 3 rectangles. Right? So we're going to approximate the area under a curve by dividing it up into rectangles. Now what's going to happen and what we're going to find is that the greater the number of rectangles, the more rectangles that we use, the more accurate our approximation gets. Right? And if we take the number of rectangles and push that out to infinity, we find that we end up with the exact area under that curve. Okay? So you might be wondering what I'm talking about here about approximations. So let's go in and take a look at another drawing, a better drawing to show this. Suppose that we had a function that was steeply increasing. So here's our function f of x. Okay? And we are asked to calculate the area between a and b. And let's say that they just say that n is 2 for 2 rectangles. So if I were to divide this in half, how do I know where to square off the rectangles? Well, traditionally, there are 3 techniques that we use quite often. Right? One is to use the left endpoints, or left rectangles. Left endpoints would be to take a look at each rectangle and use the leftmost edge of that rectangle to measure your height. Now, if I do a left approximation or use left rectangles here, I'm missing all of this area. So I've got a gross underestimate going on here. Right? Now, another technique that is used is to use, and I'll leave this in blue, I'll use pink for the one, would be to use the right endpoints. Now, the right endpoint says use the rightmost edge of the interval to find the height. So the first rectangle's right edge would be there. The second rectangle's right edge would be over there. And then when I perform that calculation, all of this is an overestimate. Right? Now, this is not to say that lefts are bad and rights are good. This is just to illustrate that there are issues with this technique as an approximating technique. Okay? When you only use a few rectangles, you get lots of bad information because there's either a lot of underestimate or there's a lot of overestimate. Sorry about that, I deleted my function. Okay? But what if, instead of lefts or rights, we wanted to split the difference and use, what color will I use? I'll use green for this. Midpoints. Well, midpoints would say go to the middle of the interval and use that as your height for your rectangle. Well, now you've got a little bit of over, and you've got a little bit of under, and maybe those will balance themselves out. But depending on how that function is changing, they're not always going to balance themselves out. They're not always going to say that, oh, the yellow is the same size as the blue. The overestimate area is the same size as the underestimate area. You just end up with something where, well, it might work, it might be better. Who knows? The way to actually make it better is to use more rectangles. Because if we increase the number of rectangles, the size of those pieces that are incorrect, the size of that error, is going to get smaller and smaller and smaller. And when you get to Calc 2, what's going to happen is, in Calc 2, you're actually going to calculate the error, and then you're going to find a way to work backwards. And what I mean by working backwards is you're going to find a way to say, okay, if I'm willing to accept 2% error, how many rectangles will I need? Which, when you stop and think about that, is actually pretty cool. All right, so what are we doing? Our job today is to find the area bounded by a curve, the line x equals a, the line x equals b, and the x-axis, the area bounded by a curve. We're going to use a technique called a Reimann summation. Reimann summations are an approximation technique that is found by splitting the area up into approximating rectangles. More rectangles, better approximation. More rectangles, more work. So the more rectangles you use, the better your approximation, but the more rectangles that you use, the more work you have to do. So it's a balancing act between doing enough work to get a good enough answer and doing few enough rectangles that you're not doing too much work. Okay? Now, there is nothing about this process that requires the next step, but it does make it a little bit easier. For our work, we are going to be working with rectangles that have the same width. So in order to get the width to be the same, we are going to say that the width of the rectangle, and we're going to use the notation delta x, or the change in x, to represent the width of the rectangle. And we are going to find it by taking b minus a. And what b minus a will do, and I'm going to draw an arrow here so you can see, b minus a will give us the distance between a and b on that number line. For example, and if this was 2 and this was 5, then how far apart are they? There are 3, because 5 minus 2 is equal to 3, and it gives you the width. Right? We divide it by n, because n is the number of approximating rectangles. Sorry about that. The number of approximating rectangles that we're going to be using. Okay? All right, now if you're wondering where 2 and 5 came up, if you're hung up on that, I made those numbers up. Okay? Now, whether you measure the height using left endpoints, lefts, right endpoints, rights, or midpoints, doesn't matter. It's the same formula for the width every single time. The width is always delta x, and the width is always found by b minus a divided by n. Now, I know this is a lot to comprehend, but let's take a look at an example to begin with. Right? Maybe it'll make more sense when we put some real numbers on it. So our job is to find the area. This is example number 1 here that I'm working on. My job is to find the area of the region bounded by the graph of the function, and in this case our function is y equals x squared, the x-axis, and over the interval 0 to 1, and notice this right here, what does this tell me? To use 4 rectangles, or if I put it into the language of Reimann summation, n is equal to 4. So I always like to make a quick sketch to see what I'm looking at here. Right? I'm working with the function y equals x squared. So there's the function y equals x squared. It's a parabola with a vertex at the origin. The interval is from 0 to 1, so starting here at 0, stopping right here at 1, they want me to find this area, and I'm going to highlight it in blue. They want me to find this area right here. Now it looks like a triangle, but it's really not, because that top edge is not straight. That top of that is curved. So it's kind of like a triangle, but it's not really a triangle. Right? They want me to find the area by breaking this up and using a Reimann summation with 4 approximating rectangles. So I need to figure out what it is I have to do to make this be 4 rectangles. Right? Now, nowhere in here does it state that the rectangles have to have the same width. We do that to keep things simple. Right? So how wide will each rectangle be? So delta x is the width of each rectangle. And what's the formula for delta x? The formula is always b minus a divided by n. And for this problem, what are we looking at? We are looking at a is equal to 0, b is equal to 1, and n is equal to 4. So our delta x is going to be 1 minus 0 divided by 4, or 1/4. Okay? Now, if you came over here and actually did the geometry of that and split this up into 4 equal pieces, that's exactly what you'd see. This would be 1/4, this would be 1/2, this would be 3/4. Okay? And then these strips right here are going to break this up into 4 equal width pieces on the x-axis. Now, how we measure the height hasn't been determined yet, but essentially we're going to measure the height using either left endpoints, right endpoints, or midpoints. Right? But what I know right now is that each rectangle has a width of 1/4. Now, down here in part A of the problem, they ask us to do this using right endpoints, meaning I'm going to set my first rectangle to have this height, my second rectangle to have this height, my third rectangle to have this height, and my fourth rectangle to have that height. Okay? So, some notation we're going to use here is we're going to talk about finding the right endpoints, and so we are going to do a Reimann summation with n is 4 and right endpoints. But I know what you're thinking. Isn't there shorthand for that? There is. The shorthand we're going to use is a capital R, and a subscript 4. Capital R for right, subscript 4 for 4 rectangles. Implied in that is this right here, that every rectangle will have that same width. All right, so here we go. We're going to do R4, R sub 4 actually. So R sub 4 says add up the 4 rectangles. How do you find the area of a rectangle? Well, the area of a rectangle is base times height, but every single one of our rectangles has the same base. They all have a base of 1/4. Now the heights are going to change. The heights are based on the functional value of the right endpoint. So R sub 4 is going to look like this. 1/4 times f of 1/4 plus 1/4 times f of 1/2 plus 1/4 times f of 3/4 plus 1/4 times f of 1. Well, so where did I get these from again? Okay. Well, the problem told me to use the right endpoints, and the right endpoint of each of those intervals are right there on that number line. 1/4, 1/2, 3/4, 1. Okay. Now evaluate. Now, you know me, lazy. Do you see how there's a common 1/4 in all 4 terms? I am going to factor that out. And now I'm going to find f of 1/4. F of 1/4 is 1/16. F of 1/2 is 1/4. F of 3/4 is 9/16. And f of 1 is 1. If you're wondering where I'm getting those values from, it's the function. The function says that the y, the height of the rectangle, the y value, because we're on that curve, on that right endpoint, is just the x value for that endpoint squared. Now I got to figure out a way to add all this up. Looks like we need to get into 16ths. So this is going to be 1/4 times 1/16 plus 4/16 plus 9/16 plus 16/16. Let's see, what is that? 9, 10, 14, 14, and 16 is 30. 30/16 times 1/4. So we've got 1/4 times 30/16. Let's see, 30/16, 1/4, half of 30 is 15, so 15 30-seconds. Is that what we're looking at there? 15 30-seconds. So the area under the curve. So the area is approximately 15 30-seconds square units, whatever those units mean. Okay? Now, some things to note about this. This is an overestimate. It is not an overestimate because it is right endpoints, but this is an overestimate. Right? All of this space right here that I'm shading in yellow, we're measuring all that and counting all that, and that really shouldn't be there because it's an overestimate. But because this is an increasing function and we used right endpoints, we ended up with an overestimate. Right? How could we make this better? Well, the easiest way to make it better is to use more rectangles. More rectangles means less wasted space, less error. Right? That was part A of the problem. What does part B ask us to do? Part B says do it again, but now use left endpoints, or if you want to be more specific, L sub 4. Okay. What does L sub 4 mean? Well, the L says use lefts, or the left endpoint of all of these, and the sub 4 means use 4 approximating rectangles, just to make it easy so I don't have to keep sliding the thing up and down and up and down and up and down. Again, we're looking at this function. We're working from 0 to 1. We broke it up into 4 pieces, but now we're going to measure every single one of them based on the left endpoint. So square it off at the left endpoint. There's my last rectangle. There's my other. And my first rectangle, the left endpoint is the origin. So that first rectangle doesn't have any height. Right? Delta x, the width of all these rectangles, is still the same. 1 minus 0 divided by 4, 1/4. Right? So now what is L sub 4 going to be equal to? First rectangle, 1/4 times f of 0, plus second rectangle, 1/4 times f of 1/4, plus third rectangle, 1/4 times f of 2/4, which is 1/2, plus the fourth rectangle, 1/4 times f of 3/4. Now, if you're wondering where those values came from again, if you're wondering where the 0, the 1/4, the 1/2, and the 3/4 came from, go back to the drawing. Okay? This is 0. This is 1/4. This is 1/2. This is 3/4. And of course, that there is 1. Okay? So the first rectangle, the left-hand edge point, oh, but wait, we're not done, because what do we get to do down here? We get to do the same thing again using midpoints. Okay, this one's going to be trickier, so I'm actually going to redraw the picture, and I'm going to try to draw it a little more accurately. The reason this one's trickier is when we're working with left endpoints and right endpoints, we can use the width, oh, that's a horrible parabola. We can use the width, delta x, to make things make sense a lot easier. Because the width allows me to find these values really quickly. I can go, this is 1 width, this is 2 widths, 2/4, which reduces to 1/2. This is 3 widths, 3/4, and that's 4 widths. But if my job is to use the midpoints, now I've got to find the value that is halfway between, and then find the height at each of those so that I can square these things off and make them into rectangles. Right? So what are those sample points? Did you hear that term I used? What are those sample points that we're going to use? Well, the sample points are the midpoints. And how do you find the midpoint of an interval? Well, to find the midpoint of the interval, you add the endpoints, divide by 2. Okay. So that means that our sample point sub 1, to see the notation I'm using, I'm calling it an x because it's on the x-axis. I've got a subscript 1 because it's the sample point from the first rectangle. And in the exponent position, I'm putting a little star. And that's what tells the world, hey world, this is a sample point. This is an x somewhere in the interval that I am going to use to find the height. Okay? And so that is going to be, let's see, to find the endpoint, to find the midpoint, you add the endpoints and divide by 2. So what's 1/4 plus 0 divided by 2? 1/8. So then what's x sub 2 star going to be? Well, that's going to be the sample point in the second interval. So that's going to be the 1/4 plus the 1/2 divided by 2. 1/4 plus 1/2 is 3/8, or 3/4. 3/4 divided by 2 is 3/8. Now, you might also see a shortcut here. Once you know the first one, the distance between the first one and the second one is delta x. The distance between the second sample point and the third sample point will also be delta x and delta x and delta x. So when I come down here to find x sub 3 star, the sample point for the third interval, I could add endpoints, or I could just take the sample point from the previous one and add a width to it. And the way I add a width to it is I take 3/4 plus, what was the width again? 1/4, 3/4. Jeepers creepers, man. Did I write 3/4 right there? I know I said 3/8. I could take the last midpoint and add a width to it. So 3/4 plus 1/4, that's what, 5/8. And we would get that x star sub 3 is 5/8. And then what will be x star sub 4? Our sample point for the fourth one. Well, that's going to be the previous 5/8 plus a width, or 7/8. Right? All right, so I'm throwing a lot of terminology and notation at you. Sample points. Sample points tell us what we're using to find the height. Sample points can be lefts, sample points can be rights, sample points can be midpoints. In fact, if you wanted to, sample points could be third points, meaning a third of the way into the interval, if that's what you wanted to do. Right? All right, so let's go ahead and calculate this. I want to find m sub 4. So that's going to be 1/4. And now I'm going to be lazy. Since I noticed a pattern, and I'm always factoring out that 1/4, I'm just going to do it to begin with. F of 1/8 plus f of 3/8 plus f of 5/8 plus f of 7/8. So that's 1/4 times 1/64 plus 9/64 plus 25/64 plus 49/64. And because I'm feeling super lazy, I'm actually going to grab a calculator to figure that one out. So let's see. What's 1 plus 9 plus 25 plus 49? That's 84. Divide that by 4, and I get 21/64. Now, is this an overestimate or is it an underestimate? Well, the correct answer is I don't know. Because there are little pieces of underestimate and there are little pieces of overestimate, but I will tell you that my picture is not even close to accurate enough to be able to go, oh, clearly the blue is bigger than the yellow, so it's an overestimate. Or clearly the yellow is bigger than the blue, so it's an underestimate. The reality is my drawing is nowhere near accurate enough to know, so I don't know whether it's an overestimate or underestimate, but what I do know is it's probably pretty close to the actual answer. Okay? All right, so I'm going to end this video here. I'll pick up for example number 2 in the next video.